Hi everyone, thanks for tuning in. So in this video we're going to be working through the notes for section 5.1 which deals with estimating area and distance. So a little bit of a summary here. So oops, immediately just scribbling right at the beginning. So a bit of a summary here. Last class we were looking at section 4.8. So this was dealing with antiderivative. So when you're given the derivative of a function and you want to go backwards and find the original function, that's when you take the antiderivative. We also were introduced to some new notation. So this is integral notation, which represents the antiderivative. And so that's that symbol that looks like a long stretched out S, and it's always paired with a d something, often dx. So that was the notation that we saw. Today, it's going to seem like we're switching gears entirely, and that's okay. So you can kind of forget about antiderivatives a little bit for today's class, although it will come up in an example on the last page. Today we're going to be exploring ways to approximate the area under a curve, and we're going to relate it back to distance. But in general, looking forward in this course, we're actually going to be relating this concept of area to the antiderivative. So it's not as though we've totally switched gears right now, even though for the next couple of sections it might seem like we have. Eventually this is actually going to be related back to the antiderivative and what we did in section 4.8. So for today, though, we're looking at how to approximate area. How do we calculate the area of something that maybe isn't a nice shape? So let's, oh my goodness, I did it again. Let's consider this example here. So let's consider the function f of x, which is given below. It's this blue curve that's been drawn. And the question is, how can we determine the area under the curve? And so when we say in this class, when we say under the curve, what we really mean is the area between the x-axis and the function. And so sometimes that might be below the x-axis and between the function and the x-axis. Sometimes it might be above, depending on where the function is. But when we say the area under the curve, we just mean the area between the x-axis and the function. And so in this example, imagine we're trying to compute the area under the curve on the interval -4 to 0. So let's actually just draw in what that area would look like. So I'm looking for this area here. And so if we look at this curve, I mean, it's not really any nice shape that we know, right? It's not a rectangle, it's not a triangle, it's not a circle, it's not a semicircle, you know. So we don't really actually have a nice geometric formula to compute it. And so this is something that I've sort of mentioned below. So since we don't have a nice geometric formula for the area, we're going to need to approximate the area under the curve. And there's actually a lot of ways of doing this. So one way you could possibly, look at all the full squares that are under the curve and count those, and then you could roughly, say, okay, well, these two squares are roughly 1. And so you can kind of eyeball it and try to guess the area that way. But another method, and the method we're going to be focusing on in this course, is we're going to use a shape whose area we know, and we're going to draw that shape sort of encompassing the area of this parabola. So one way to approximate the area is using rectangles, because that is a shape where we know how to find the area of it. It's length times width or base times height. You can think of it either way. So I'm just going to draw maybe a little picture to illustrate what I'm saying here. So let's try to sort of draw roughly the same curve that we had above. It really doesn't matter though. It doesn't have to be pretty. So this is -4 to 0, and we're trying to approximate this area. The height of the high point is roughly 4. And so one thing I could do is I could draw, a box that goes from, a square that goes from -4 to 0 on the x-axis and 0 to 4 on the y-axis. And I could say, okay, well, this square is definitely bigger than this. The area of this rectangle is bigger than the area under my curve, but it's, not so much bigger. So it's an approximation. So we could say that the area is going to be approximately equal to the base times the height of this rectangle. Its base length is 4. Its height is 4. So I could say my area is roughly 16 units squared. And is that a great approximation? No, but it is approximating the area under the curve. And so what we're going to see is that you can actually do it using more than one rectangle. And when you use more rectangles, the approximation becomes a lot more accurate. And so we're going to outline 3 different rectangle methods for approximating the area. So the first method that we're going to outline is called the left endpoint approximation. And so the way that this method works is the first step is you take the interval that you're trying to approximate the area between, and you break it into a certain number of equal pieces. So I called it n, and that will always be specified to you in a question. So I would say, you know, break the interval into 6 pieces, or 10 pieces, or maybe 2 pieces. And so you break the interval into n equal pieces. So the equal part is really important here. You want to make sure that each little subsection of that interval is the exact same size. Then, after you've done that, you want to make n rectangles, and so the base length of these rectangles is going to be determined by the length of your subinterval. So if you divide, let's say, 5 things in, an interval of length 5 into 2 pieces, then each piece would be 2.5, right? 2 equal pieces would each be length 2.5, and that's going to be the base length of your rectangle. The height of the rectangle in the left endpoint approximation method is determined by the height of the function at that left endpoint of each subinterval. So we'll see this when we go through an example, but basically each sort of subset, you're going to have a left endpoint and a right endpoint. You're going to take the left endpoint and look to where the function is, where's the y value of the function at that left x value. And that y value of the function is going to be your height of the rectangle. Then what you do is you add up all of the rectangles that you drew around the curve, and that's going to give you your approximate area of the entire curve's area. And the more rectangles that you use, the better the approximation actually ends up being. So we're going to do maybe an example where the approximation number is not great. So we're going to use n equals 4 left endpoint rectangles to approximate the area under the curve f of x. So we're using the same function again, and we're going to approximate the area between -4 and 0 using the left endpoint method. So first of all, we want to divide the interval 0 to -4 into 4 equal pieces. And so if we do that, it's actually quite nice. So here's 0, here's 4, and we want to divide it into 4 equal pieces. So I'm going to put lines at all of the integers, right? So -3, -2, and -1. And these are 4 equal pieces. And so my first rectangle is going to be on the subinterval -4 to -3. My second rectangle will be between -3 and -2. My third rectangle between -2 and -1. And my fourth rectangle between -1 and 0. Now to determine the height, we'll start off with our first rectangle here. So my subinterval, if you will, is -4 to -3. That's my first interval that I'm dealing with. And so I want to take the left endpoint on that interval. So the left one would be -4. The right one would be -3. So I take the left endpoint -4, and I use the height of the function at x equals -4 to determine my height of the rectangle. Well, my function at x equals -4 is actually 0. So that means the y value for my rectangle is going to be 0. So my height of my rectangle is 0. So I'm just going to draw a flat looking rectangle between -4 and -3, and that's going to be my first rectangle. For my second rectangle, between -3 and -2, well, the left endpoint is now -3. And the height of the function at x equals -3 is up here. And so that is going to be the height of my second, oops, that's not very good, of my second rectangle. You will definitely want to take a look at my filled in notes that I've posted to CoreSpaces for this section, just because it's quite hard to draw these with a stylus. Okay, rectangle 3 on my interval -2 to -1, well, now my left endpoint is -2. So I take my height of the function at x equals -2, and that's going to give me the height of my third rectangle. Then at x equals -1, that is now my new left endpoint between -1 and 0, so it's going to give me the height of my rectangle between -1 and 0. And so filling this all in, I'll just sort of shade in my rectangles. This is now approximating the area under the curve. And so it's tough to say if this is a better approximation than the one I drew on the other page, but it's the one we're going to do. So how do we do this going forward? Well, the next step after we've drawn our rectangles is to compute the area of each of the rectangles. So area 1 of our first rectangle, well, the formula for the area of a rectangle is base times height. The base length of every single rectangle, because we've divided it into equal pieces, is 1. And the height of my first rectangle is actually silly, it's 0. So my first rectangle actually has area 0. My second rectangle, again, it's base times height, and my base is still 1. The base length is actually the same for every single rectangle because we designed it that way. We broke it into equal pieces. And my height, I just had to eyeball this, and I thought that it looked like it was roughly at 2.2. So I said I had a rough height of 2.2, so my area becomes 2.2. Then for area 3, rectangle 3, so again, our base length is 1, and my height, I said, was approximately, just by eyeballing it, was 3.8. Then for the fourth area, it's 1 times 3.9. So I said roughly the height was 3.9 for that area. And then, so now I have my approximate areas for the 4 rectangles. So my overall approximate area is going to be adding up these 4 rectangles areas. So 0 plus 2.2 plus 3.8 plus 3.9. And this is going to equal 9.9. So that's my approximation using the left endpoint method. So then there's also another method called the right endpoint approximation method. And so this is almost exactly the same as the left endpoint approximation method, except instead of using the left endpoint on each of our subintervals, we're going to use the right endpoint on each subinterval. So same exact method, oops, sorry about that, same exact method, but using the different endpoint. Okay, so in my first, so I'm going to break up my -4 to 0 into the same, oops, that's not very good, into the same 4 pieces. And now I'm going to use the right endpoint. So between -4 and -3, my right endpoint is going to be -3 this time. And so my height of my first rectangle is going to be at the y value at x equals -3. So my first rectangle is actually going to look like this. For my second subinterval, -3 to -2, well, now if I take the right endpoint, that's going to be at x equals -2. So my y value at x equals -2 is up here. So that's going to determine, that's going to be my height for my second rectangle. Oh, this is so hard to draw. Okay, rectangle 3 between x equals -2 and x equals -1. Now my right endpoint is at x equals -1. So my height is going to be determined there. And at x equals, between x equals -1 and 0, my right endpoint is at x equals 0. And so that's going to determine my height. So shading this all in, the area of these 4 rectangles will approximate the area under the curve. And let's add up their areas to do so. So the first area, the first rectangle, same formula, base times height, and notice our base length doesn't change. Even though the endpoints changed, our base length, we still cut it into 4 equal pieces, so our base length is still 1. And my rough height, we already actually eyeballed this on the other page, is roughly 2.2. So my first area is 2.2, which is probably better than an area of 0. My second area for base times height, again, base length is 1. My height is 3.8. So overall area is 3.8. Then third area is 1 times 3.9. It's 3.9. I know this isn't too exciting. And then my fourth area is 1 times, and I said that roughly the y value at x equals 0 was roughly 1.3. So this area is 1.3. So my total area, approximately, when I add up these 4 numbers, so I'm just going to say 2.2 plus ... all the way up to adding up 1.3, is 11.2. So we can see that the right endpoint approximation, in this example at least, gave us a larger approximated value than the left endpoint approximation. Okay, so there's one more method that we use to approximate these rectangle areas, and so the last one is called the midpoint approximation method. And so you can probably guess already what this is going to be. So in the midpoint approximation method, same exact procedure, except we use the midpoint of each subinterval to give our height of the rectangle. So let's actually work through this example really quickly together. So on the interval -4 to 0, we're still, chopping it into 4 pieces. So the same 4 spots are our subintervals. But now we're going to use the midpoint. So between x equals -4 and -3, which is our first subinterval, we're going to use the y value at x equals -3.5. So that y value is actually going to give us our rectangle. And notice our rectangle is still has the same base length. So I use the middle point, but I extend my rectangle to the left and to the right by half a unit, so that I still end up with a rectangle with base 1. So it's still on the subinterval -4 to -3, but its height is determined by that midpoint's y value. Between -3 and -2, I want to use the midpoint -2.5, and I'm going to use the height of the function at x equals -2.5 to give me the height of my rectangle. Between -2 and -1, at -1.5, I'm going to use that height to give me the height of my third rectangle. And between -1 and 0, I'll use the height at x equals -0.5 to give me the height of my fourth rectangle. And so when you shade this in, you can actually visually see that the midpoint approximation method is actually, it's our most accurate. It's going to be the one that most closely resembles the area under the curve. So it's actually probably the best method of the 3. And so when we add up their areas, area 1, I'll do this pretty quickly. So it's base times height. The base length, like I said, in the midpoint method, any method, it doesn't matter which method you use, the base length is always determined the same way. And so here the base length is 1 because we divided an interval of length 4 into 4 equal pieces. So each piece is length 1. The heights are what are a little bit different here, and I just eyeballed them. So I thought roughly the first midpoint's height was at 1.3, so that gave us an area of 1.3. For the second rectangle, I said the base length obviously was 1, and I roughly approximated the height to be 3.1. For the third rectangle, I roughly approximated our third height to be 4. In fact, that one is the one that probably was the most accurate. And for the fourth rectangle, I said the height was probably about 3. So adding these 4 numbers up together gives us our new approximated value, and I get that the total is 11.4. So that's the midpoint approximation. And regardless, the more rectangles I added in, the better this approximation would be, but you can see it gets tedious pretty fast adding up a whole bunch of rectangle areas. So let's work through an example together. So in this practice question, actually first and foremost, these options are all wrong. None of them are correct. So just cross them out. We'll keep it from being a multiple choice question. So we want to use n equals 3 rectangles to estimate the area under the curve of the function f of x equals 2x squared plus 4x. And we want to do this on the interval 1 to 4 using the midpoint method. So you might think that you need to be able to draw this curve, this parabola function, and then draw the rectangles underneath it in order to find the area of these functions, or in order to find the height of each of your rectangles. But you don't actually need to be able to draw the function. So the way that I do it instead is I just draw the interval that we're concerned with. So this is 1 to 4. And we want to break it up into 3 equal pieces. So if we break it up into 3 equal pieces, that's going to be actually nice. It's going to be at the integer values, 2 and 3. And if we want to use the midpoint of each of these subintervals, so our first subinterval is 1 to 2, our second subinterval is 2 to 3, and our third subinterval is 3 to 4. If we want to use the midpoint of each of these subintervals, that's going to be at each of these spots here. And so let's call them maybe midpoint 1, M1, midpoint 2 is M2, midpoint 3 is M3. That doesn't really look like a 3. Let's try to fix that. Third one, sorry, someone in my building is listening to music. It's very distracting. Okay, so midpoint 1 is at 1.5, midpoint 2 is at 2.5, midpoint 3 is at 3.5. Okay, so then what we do with this is we want to compute the area. So you can imagine that we have some sort of rectangle that is between 1 and 2, and its height is determined by the function's height at 1.5. So how do we figure out what the function's height is at x equals 1.5? Well, we actually know what the function is. We actually know that the function is 2x squared plus 4x. And so if we want to find the y value of the function, we just need to take x equals 1.5 and plug it in to f of x in order to do so. So our first area, area 1, is going to be base times height. Well, what's the base length of each of these rectangles? Each one is of length 1 because we took an interval of length 3 and we divided it into 3 equal pieces. So our base length is 1 again. And for our height, we want to take f of 1.5. And so to do so, we get, 1 times, I'll show it 1 time. So when we take 1.5 and plug it in, we have 2 times 1.5 squared plus 4 times 1.5. And we end up with 10.5. Then for the second area, base times height, well, again, our base length is 1. And our height is determined by the y value of the function when x is equal to our second midpoint, which is 2.5. And so when we work this out, we end up with 22.5. For our third and final rectangle, our base times height ends up being, again, 1. And our y value, or our height, is going to be f of our third midpoint, so f of 3.5. And that works out to 38.5. So our overall area approximation involves adding up these 3 numbers, the 3 rectangle areas, so 10.5 plus 22.5 plus 38.5, and we end up with 71.5. So that is our midpoint approximation, and even though we're not picturing the curve, we could still do it just by plugging into the function because we know that that gives us the y values. Okay, so we're going to move on to a little bit of an application here for the last page and a half of these notes. And so we're going to be talking about distance traveled. So to begin with this example, let's suppose that we had the velocity function, so v of t, of a car that was moving down a highway, and we wanted to determine how far the car had traveled between time t equals a and t equals b. So in order to do this, we would actually want the distance function, right? We'd want the position function of the car. We currently have the velocity function, but we want the position function. Well, let's think about the relationship between these two functions. The position function is the original function, and the velocity is its derivative. So this is a scenario where we have the derivative function, but really we want the original function. So this is a perfect scenario to use antiderivatives, to go backwards. So what we could do is we could take the antiderivative of our velocity function, which would have us determine s of t, it would have us determine the original function. And then the distance traveled, we would take s of b minus s of a, right? We'd take how far you were at the final time point minus how far you were at the starting time point. And that would give you the distance that you traveled. So let's work through an example together. So we have the velocity function v of t is equal to 2t minus 0.5. And we want to determine the distance traveled between t equals 1 and t equals 3 seconds. So we'd like to first and foremost find our position function s of t. And we know that that's going to be the antiderivative of our velocity function, which is 2t minus 0.5. Now, because the variable is t and not x, I actually want to put dt here instead of dx. But again, that integral symbol and that dt, they have to both be there at the same time. So now that I'm ready to take the antiderivative, I'm going to drop the integral sign and the dt, and I want to take the antiderivative of 2t squared. So 2t. So let's remind ourselves what we do. So to take the antiderivative of this t, we want to increase its power by 1. So now it's going to be to the power of 2. And we want to divide by that same power. So it's 2t squared divided by 2. Then for minus 0.5, what function has derivative minus 0.5? Well, minus 0.5t has derivative minus 0.5. And then last but not least, we add a constant to it. So we could simplify this a little bit by crossing out those 2's that cancel. And then if we wanted to compute our distance at 3 seconds, we'd compute s of 3. And so plugging in, we'd get that it's 3 squared minus 0.5 times 3 plus a constant. And then that would work out to being 7.5 plus c. S of 1. We plug in 1 into our function, so 1 squared minus 0.5 times 1 plus a constant, and we end up with 0.5 plus c. And so if we want to compute the total distance traveled, we would take s of 3 minus s of 1, and we end up with 7.5 plus c minus 0.5 plus c, which is equal to 7. Okay, so that's our example. That's one way of approaching it. But what we'll see on the next page, on the final page, page 6, we start off with a question. And so this question is, what if we actually didn't have the equation of the function v of t? So in the last example, let's scroll back for a second, we actually knew that v of t was equal to 2t minus 0.5, and that allowed us to find the antiderivative. So the question posed here is, what if we didn't have that actual equation, but rather we had only its graph? How could we determine the distance traveled then? And so the answer is that we can actually approximate the distance in a similar way to how we approximated the area under the curve. So you may be wondering, well, what's the relationship between area under a velocity curve and the distance function? You know, those seem like they shouldn't be related to each other, but they actually are. So let's remind ourselves of the distance formula. Our distance formula tells us that velocity is equal to distance divided by time. So that's the same thing as saying that distance is actually equal to time times velocity. So let's think about this for a second here. So the base length of each rectangle is going to represent time. If we were to graph velocity on the x-axis, we would have time. And so the x-axis, those little subintervals, that gives us the base length of a rectangle. So time is going to actually represent our base length of the rectangle. And then what would the height, if we've graphed velocity, our height of the rectangles, which just come from the y values of our function, well, our heights would then be the velocities. So what we actually have when we're taking the area of these rectangles underneath the velocity function, what we're actually doing is taking our base length, which is time, and multiplying it by our y values, our heights, which is velocity. So we're taking time times velocity, which is going to give us distance. So this is why the area under the curve is actually, under the velocity curve, relates directly to the distance function, because it actually, the area under the velocity curve is the distance, because it's time multiplied by velocity, which is distance. So let's work through an example. So the function below represents the velocity of a moving particle at time t seconds. And we want to estimate the distance traveled by the particle between t equals 1 and t equals 5 seconds using n equals 2 left endpoint rectangles. So we're going between t equals 1 and t equals 5. And so we want to divide this interval, which has length 4. We want to divide it into 2 equal pieces. So that means we're going to put the dividing line at x equals 3. So we have one interval between 1 and 3, and one interval between 3 and 5. And so we're trying to use the left endpoint method. So that means on my interval 1 to 3, I want to use the height of my rectangle to be determined by x equals 1's height. So my velocity at time 1. And so I'm going to draw a left endpoint rectangle here. Pretend that's a straight line. And then on the interval 3 to 5, I want to use the left endpoint. So that means I'm going to take my velocity at x equals 3, and that's going to give me my height of my second rectangle. So the area of these two rectangles roughly approximates the area under the velocity curve. It's not a great approximation, but it is a rough approximation. And so my first rectangle, A1, its area is base times height again, while our base length is 2 seconds. And our height is going to be our velocity, right? So our velocity here I said was roughly 0.4, and I don't know what the distance unit is. Let's actually just make one up for this question. Let's say the moving particle is, going t seconds, and let's say it's in centimeters, just to give ourselves a unit. So we're going to say it's in centimeters. So then our velocity here, I'm saying it's, our height is roughly 0.4, and that's going to be, it's a velocity, it's a derivative. So remember, there's always a rate attached to this, and so we would say it's centimeters per second. And so what you can see is happening here is the seconds are actually going to cancel. And so what we're left with is a distance. We're left with 2 times 0.4, which is 0.8 centimeters. Then for our second area, A2, we have base times height. Well, our base of our second rectangle is still 2 seconds long. It's between 3 and 5 seconds. And our height of our velocity curve is at 3, which means that's 3 centimeters per second, because it's a velocity, so it's a rate. So again, these seconds cancel out, and we're left with a distance, which is 6 centimeters. So then overall, we could say that distance traveled, so distance traveled, we want to add up these two areas, is we're going to say approximately 6.8 centimeters, right? And so, this isn't a great approximation. If we did more rectangles, we would get a better approximation. But here's an example of relating the area under the velocity curve to the original function, to the distance function. So already you might actually be able to see that it makes sense that there's going to be some sort of a relationship between antiderivatives and this area under the curve. And so that's what we're going to be exploring moving forward into sections 5.2 and 5.3. And then by the time we get to sections 5.4 and 5.5, we'll actually just be looking at more techniques of finding antiderivatives. Okay, so that is it for this section. Thanks so much for listening, and I'll be getting through the other lectures soon, so you'll see those posted soon. Thanks so much.